In this video, I'll show you how to build and program an 8-bit computer using a Zilog Z80 CPU and an Arduino Nano. The software for programming in Z80 assembly language is all built into the Arduino, and in a series of follow-up videos, I'll show you how to write a basic operating system and how to load software written in the C programming language. To build the project yourself, you'll need an Arduino Nano, two 74HC573 latches, a parallel SRAM chip, like a 32 kilobyte 62256, and of course, a Zilog Z80 CPU. You'll also need a breadboard at least 3 sections wide, a few resistors, and plenty of hookup wire. This project builds off of the computer bus layout from my previous video on EEPROM programming, so if you want to build it yourself, you'll want to start there first. Picking up from the last video, I'll first replace the 28C64 EEPROM with an AS6C62256 SRAM. The pinout is identical following the JetX standard for memory chips, so we can just do a straight swap. However, I do need to add the A13 and A14 address lines, which were left unconnected before. Now I can go ahead and install the SRAM chip. Next up is the Z80 CPU. First, I'll place the power and ground jumpers, and then install the CPU chip. Next, I'll hook up the data bus lines, which are jumbled around on the left side of the CPU. Then I can start on the upper lines of the address bus. Unlike the data lines, these are all in order, so they're much easier to follow. Moving on to the right side of the CPU, we have the lower lines of the address bus, which are also in order and therefore straightforward to wire up. And finally, we have the read and write enable lines in the lower right. Now that control of the computer bus is being shared between the Arduino and the Z80, we'll need to do something with the output enable pins on the address latch chips. First, I'll remove the jumpers that tied output enable to ground, then add a jumper to tie them both together, and finally wire them up to pin D2 on the Arduino so we can toggle the address output as needed. Next, we need to add some additional control signals between the Arduino and the Z80. First, we need to send a clock pulse to the CPU. I'm using Arduino pin D3, one of the PWM pins, because it can be configured to generate the clock pulse automatically. Next, I'll wire up Arduino pin C1 to the Z80 reset so we can keep the Z80 off the bus when the Arduino needs to access memory. I'll also wire Arduino pin C0 to the Z80 interrupt and pin B5 to the Z80 halt, so the Arduino and the Z80 can both signal each other while a program is still running. Finally, we'll need to add some 1K pull-up resistors to the unused input pins, NMI, BusRQ, and wait. And I'll also add a 100 nanofarad bypass capacitor to filter the power rail shared by the Z80 and the SRAM. With everything wired up, let's move on to coding the Arduino. This picks up from where we left off in the last video, so let's do a quick review of the code so far. The platform I/O INI file is set up the same as before, using the Atmel AVR platform, Arduino framework, and with options to select Nano or Uno boards. My core library is still included, but I've changed the link to a zip archive so it'll work even without the Git tool installed. And finally, monitor filters is set to direct, which will prevent the serial monitor from filtering out control characters. Moving on, at the top of main.cpp, we have the header files and imports for the I/O types, command line, and monitor functions, all included from my core library. Below that, we have the type definitions that map the Arduino I/O pins to the data bus, address latches, and read and write control lines. Next, we define the bus type that wraps the previous type definitions into a simplified computer bus interface. In the previous video, the config read, config write, and bus write functions were all written out, but here I've instead inherited from the port bus template that provides default definitions for those functions. The read bus function still needs to be defined explicitly because of how the data port needs to be reconfigured as an output in order to drive the address latches. Moving on, we have the definitions of the StreamX, CLI, and API types that are used by the command line interface. Then we have the setup function that initializes the serial interface, the setBaud command to change the baud rate at runtime, and finally the loop function with the list of commands being parsed by the CLI's run-once function. As you can probably tell, most of the heavy lifting is being done by the core library, and as in the previous video, the code we need to write will mostly involve mapping out the new I/O pins. So, without further ado, let's get started. First, let's hook up the address latch output enable that was wired to port D bit 2. This uses active low logic levels, so we wrap it with that adapter type. The address MSB and LSB latch types that we defined before take an optional third parameter for output enable. So we hook the new pin up to those, and that's it for the computer bus. I'll explain how this gets used later, but for now, let's move on to the Z80 control signals. First, we have Z80 reset on port C, bit 1, then Z80 interrupt on port C, bit 0, and finally Z80 halt on port B, bit 5. These are all active low control signals, so we wrap them with the same adapter type. Now we get to the complicated part. We want to output a clock signal to the Z80 on port D, bit 3, and while we could just toggle the I/O pin directly in a loop, a much better solution is to use the microcontroller's built-in timers. If you saw my previous video on controlling LEDs with software PWM, you may remember that I used this timer to generate CPU interrupts. This time we won't be using interrupts, and instead we'll just use the timer to toggle an I/O pin, similar to how the built-in PWM works. Configuring the timer requires modifying several internal registers, so to keep things tidy, let's start by defining the type Z80 clock to contain everything. Next, we generate core wrappers for the registers to make them easier to use. The registers we need are TCCR2A, TCCR2B, OCR2A, and OCR2B. The TCCR registers each have several bit fields inside them, so we can define types to mask off just the bits that we want to use. First is COM2B with bits 4 and 5 in TCCR2A. So we mask those bits off with hex 30 and use right align to shift them over. Next is CS2 with bits 0 through 2 in TCCR2B. So again, we mask those bits off using hex 7. Then we have WGM2. This one is split between both registers, so we'll need to use the bit extend adapter to join them together. The most significant bit is WGM22 in TCCR2B, and the least significant bits are 0 and 1 in TCCR2A. Finally, the timer also refers to pin OC2B, which is really just an alias for port D, bit 3. With all the bit fields defined, we can now write a config function to set up the timer the way we want it. First, we write mode2 to WGM2 to select the CTC mode. This makes the timer count up to the value in OCR 2A and then reset the count back to 0. Then we write mode1 to COM2B, which toggles the I/O pin OC2B when the timer matches the value in OCR 2B. But in order for this to work, we still need to configure OC2B as an output pin. Next, we set OCR 2A to 0. In CTC mode, this is the value that the timer counts up to, and setting it to 0 means that every timer tick will reset the count back to 0. Likewise, setting OCR 2B to 0 will make the output pin toggle every time the count resets. Since it takes 2 toggles to make a cycle, and since the count will reset every timer tick, the output pin ends up blinking at half the frequency of the timer clock. Finally, if we set CS2 to 1, it sets the timer clock equal to the Arduino's 16 MHz clock, and thus the clock pulse sent to the Z80 will be half of that, or 8 MHz. The Z80 that I'm using is rated up to 10 MHz, so this is just about perfect. Anyway, that should be enough to get the Z80 running, so let's continue on to the setup function. First off, we configure and enable the Z80 reset to initially hold the CPU in the reset state. Then we configure the interrupt as an output, halt as an input, and finally configure the clock. Now we can define a command to let the Z80 loose and start running code from SRAM. First, the Arduino needs to release the address bus so the Z80 can drive it instead. The config float function of the bus type does this by configuring the address port as an input, which in turn configures both of the latches by disabling the output enable pin that we defined earlier. Next, we disable the reset pin and the Z80 will start running code at address 0. The Z80 program will continue to run until it reaches a halt instruction, which pauses the CPU and pulls the halt pin low. For now, we'll just have the Arduino loop while waiting for the halt pin, but in the next video, I'll show how we can transfer data back and forth while the program is still running. Finally, we put the Z80 back into reset so the Arduino can resume control of the address bus. Finally, we can add the run command to the command list, but we still need a way to load Z80 code into memory. Fortunately, I've included a full Z80 assembler with the core library. First, include the core/mon/Z80 header file. Then we can add the assembler, disassembler, and label commands. And with that, the code is finished and we can upload it to the Arduino to try it out. To verify that everything works, let's write a simple assembly language program that adds 2 numbers together. The Z80 program starts at address 0, so we need to type that as the address for the first instruction. First, we load the HL register with address hex 100. This is a 16-bit register that acts as a memory pointer, and hex 100, written with a $sign for hexadecimal, is the address where we'll put the first number. After hitting enter, the command line is automatically filled with the address of the next instruction, so we can easily continue typing our program. Next, we load the A register with the byte addressed by HL, indicated by the parentheses around HL, signifying indirect addressing. The A register is the accumulator, where the result of math operations are stored, so this will be the first number that we add together. Then we increment HL to point to the next address, hex 101, where the second number will be stored. The add instruction then takes the second number addressed by HL, adds it to the first number, already in A, and stores the result back in A. Then we increment HL again to hex 102, where we'll store the result. Another load, but this time with the order of HL and A swapped, stores the value from the A register into the memory addressed by HL. And finally, the halt instruction ends the program and pulls the halt pin low to notify the Arduino that it can take back control of the computer bus. We finished writing assembly, so we can either use the delete key or the down arrow, to clear the command line for the next command. Now we can store the two numbers that we'd like to add into memory, starting at address hex 100. I'll use 3 and 5. Then we type the run command to run the program, and finally the hex command to read the results back from memory. There we can see the 3 and 5 that we already wrote, followed by the expected answer, 8. That was a good test to verify that the Z80 works, but not a very useful program. So let's try something a little more substantial, an ROT13 string cipher. This is a well-known encryption algorithm that works by rotating each letter 13 steps through the Latin alphabet. So ABC becomes NOP and so on. Since the alphabet has 26 letters, applying the algorithm twice, 26 steps in total, restores the original message, meaning that the same algorithm performs both encryption and decryption. First, let's write out the algorithm in C before translating it to assembly language. Since we're parsing a string of characters, we'll use a for loop. As before, I'll start the data at address hex 100, so that'll be the initial value of the character pointer. The pointer will keep incrementing until we find character 0, the null terminator, indicating the end of the string. For the body of the loop, we'll just have a series of if and else statements. In the ASCII character encoding, lowercase letters have a larger value than uppercase letters. So first we'll check if the character is larger than lowercase z, and if so, we know it's not a letter and we continue on to the next character. Then we check if it's greater than or equal to lowercase n. If so, it must be a letter and we subtract 13 to rotate it. Likewise, if it's greater than or equal to lowercase a, it's also a letter, but instead we add 13 to rotate it. Next, if we didn't match the above cases, but the character is greater than uppercase Z, it must not be a letter, so we continue on to the next character. Then, if the character is greater than or equal to uppercase N, we know it's a letter and we subtract 13 to rotate it. And finally, if the character is greater than or equal to uppercase A, we know it's a letter, but this time we add 13 to rotate it. Now that we have the whole algorithm in C, it'll be a little easier to translate it by hand into assembly. As before, the assembly needs to start at address 0, and we'll start by loading the pointer address into HL. However, instead of using hex 100, let's subtract 1 and use hex FF. The reason is because I'd like to do the pointer increment at the top of the loop, which tips the initial value back up to hex 100. Since the increment is the top of the loop, and because we'll need to branch back to it later, we use the label command to tag this address with label next. Now we need to check if we reach the end of the string. First, load the value at address HL into register A. Then use the CP instruction to compare register A with value 0. If register A equals 0, the Z flag will be set, but what we really want to do is skip forward to the loop body if the Z flag is not set. So we can use jump relative if not 0, but we don't know the address to jump to yet. So we'll just put 0 for now. If we made it to the next instruction, instead of branching, it means that we reached the end of the string. So we end the program with the halt instruction. At the following address, we can continue with the rest of the loop. Let's save this address as label body. Now we can go back to the previous jump instruction, using the up arrow to scroll through history, and replace the temporary address with label body. Before moving on, let's define subroutines for adding and subtracting 13 so the following branches can just jump there. First, let's put add 13 at address hex 30. We'll assume that the letter is already in the A register and use the add instruction with value 13, then store A into address HL, and finally jump relative to label next. Let's do the same thing with label sub 13 at address hex 40. Subtract 13 from A, store A into address HL, and jump relative to label next. Now we continue with the body of the loop back at label body. First, we test if the letter is greater than lowercase z. It's easier to test less than, so we swap the order and load z into the A register, then compare A with the letter at HL. If the letter is greater, the carry flag will be set, so we use jump relative if carry to label next. Then we load the letter back into the A register and compare with lowercase n. If the letter is greater than or equal, we use jump relative if not carry to label sub 13. Likewise, we compare with lowercase a, and if the letter is greater than or equal, we use jump relative if not carry to label add 13. Next, we test for greater than uppercase Z, but again, it's easier to test for less than, so we load Z into the A register, compare it with the letter at HL, and branch with jump relative if carry back to label next. Then we load the letter back into the A register, compare with uppercase N, and jump relative if not carry to label sub 13. Finally, compare the letter with uppercase A, jump relative if not carry to label add 13, and otherwise jump relative to label next to continue the loop. The program is now finished, so we can write an encrypted string at hex 100, followed by a 0 for the null terminator, then run the program, and read back the result at hex 100. Finally, I have a special message for everyone who got this far. Liebe Herr Njrfbzr. It's not a chant to the elder gods, it's just an encoded string that you can read with this project. And don't cheat, or Njrfbzr will take you away to a frightening liminal space between states of being. Anyway, that's it for this video, so don't forget to like and subscribe if you'd like to see more. As always, thanks for watching.